Today we're going to do some basic sketching of polynomial functions in general. So I'm going to break it down into a few simple steps, but whenever you sketch a polynomial function, we're going to go ahead and start with this one right here. Essentially, the first thing we want to do is we want to determine the end behavior of the graph, okay? So remember, we can determine, we say determine end behavior. And we're going to do this by looking at the leading coefficient and degree. So we say look at the LC and degree, that we call this a leading coefficient test, okay? So when we talk about the leading coefficient here and degree, we say, well, the degree of this thing, if we're going to write this down, we say it's the third degree. So it is a cubic thing, and then we say, what is the leading coefficient? And so we say the leading coefficient here is this 1 out in front of this x cubed. So we say leading coefficient is 1, and so we're going to say that this is positive. Also, the third degree, I want to say that this is an odd degree. What this allows us to do is to say, well, since my leading coefficient was a positive 1, on the right side of my graph, it's going to end upward. And since it was an odd degree on the left side of my graph, it must have started downward. So I've already got an inclination that I've got this curve that starts down here on the left and goes up to the right. So now what we're going to do is we're going to plug in some extra x values to find some points that lie on this graph. Now, plugging in extra x values can be something that is not an easy task, or at least it's not very straightforward because you have to do direct substitution on a lot of stuff, or do you? So in terms of what x values to use, I'm going to use a nice central set of x values to plug in. I'm going to plug in easy ones first. So for instance, if I plugged in, say, 0 for x, we say, well, what is f of 0? I want everybody to notice that if I were to plug in f of 0, it'd be really easy to just go ahead and do direct substitution here. We could say 1 times 0 squared minus 4 times 0 minus 1. But you can see how whenever we do something where we're plugging in 0 for x, what we usually get left is this last term here, this constant term. So one thing we want to put here is this. We say 0, negative 1. But on any polynomial function, the constant term, this is the y-intercept. And this is like always true when you're talking about polynomial functions. So we already know it hits at the point 0 and negative 1. Another really easy x value to plug in would be 1. So we say, let's go find f of 1. So we can see how this would be, 1 to the fourth plus 1 to the second minus 4 times 1 minus 1, where you get 1 plus 1 minus 4 minus 1, which is 1 plus 1 is 2, minus 4 is negative 2, minus 1 is negative 3. So we'd say, well, negative 3 here. This is on my graph, so we say 1 comma negative 3 would be right here. Okay. So what we're doing here is essentially plug in extra x values to find points to graph. Find points to sketch. I'm going to write sketch, not draw, but sketch, So we're finding these extra points. The thing is, when you get to 2, we say, let's go find f of 2. It starts to become a thing where when you plug in a 2 in all these spots, it's not a huge deal, but it becomes quicker to do synthetic substitution. So we could say synthetic substitution, remember we're dropping in the coefficients of this original polynomial. So we have a 1, a negative 4, and a negative 1. So we have a 1, a negative 4, and a negative 1. And we want to evaluate when x equals 2 here. So we'll put a 2 out here, and the way this looked was we'll just go ahead and multiply diagonally and add up, vertically. So we say 2 times 1 is 2, plus 1 is 3, times 2 is 6, plus negative 4 is positive 2, and 2 times 2 is 4. And we say 4 plus a 1 here is 3. So this right here, that's what we're going to get for a y value when we plug 2 into this function. So we're going to get 3. So I'm going to take these things out. We say 2 comma 3 is also on my graph. So we say 2 comma 3. 2 comma 3 is right here. And then what if we put in, say, a negative 1? Well, putting in a negative 1, I'll just put a negative 1 here. We get 1, negative 1 times 1 is negative 1, plus this is 0, times negative 1 is 0, plus a negative 4 is negative 4, times a negative 1 is a 4, and then 4 minus 1 is 3. So this one up here, I'd get 3 when I plugged in negative 1. So we get 3. And then when I plugged in negative 2, let's see, when I plug in a negative 2, we get this. Negative 2 times 1 is negative 2, plus a positive 1 is negative 1, plus, or times a negative 2 is a 2, plus a negative 4 is a negative 2, times a negative 2 is a 4, and then 4 plus a negative 1 is a 3. So we get 3 again. So 3 is a popular number here. We say negative 1, comma 3 would be right here, and then negative 2, comma 3. So I want to surmise, could we think of a graph that goes through all these points from left to right? Because this is what we're going to have to do now, is plot points, and we're going to sketch a smooth curve. So a smooth curve from left to right, going through the points and adopting the end behavior that we had talked about. So adopting the end behavior. So when we talk about end behavior, what I'm saying is we already were aware by looking at the degree and leading coefficient that this ends up on the right and started down on the left. So I could think of a curve that probably is doing something like this here, coming through and then coming back around here. So this would be our smooth curve, and this would be the sketch of our third degree polynomial in general, okay? So I'm going to try this again. I'm going to sketch a graph of this. We'll go a little bit quicker this time. We say end behavior. We say degree. It's fourth. So this is even degree. And then we say leading coefficient. The leading coefficient this time equals -1, so this is negative. So what this means for us is since we have a negative leading coefficient, we're going to end down on the right side. And since it's fourth degree, we had to start the same end behavior as we do on the right side. We say start down. So now we say, what else could I tell from this? Well, we need to plug in some extra points. So extra ones to plug in. We say for now this is a good set. And easy ones to plug in at first with direct substitution would be like 0. We could say when I plug in 0, anything with an x would go away. So I notice that my constant's technically 0 out here. I'm going to get 0 when I plug in 0. And that could be easily shown. So we say 0, 0 is on the graph. We say, what if I plug in 1? Well, if I plug in 1, you'll notice that you just get the coefficients. You'll get -1 times 1 to the fourth, which is just 1, minus 2 times 1 to the third, which is just going to give us -2 here, plus 2 times 1 squared, plus 4 times 1. So I get this, essentially -1 minus 2, so -3, plus 2 is -1, and -1 plus 4 is 3. So we're going to get a 3 here. So -1 comma 3, sorry, that doesn't go there, that goes here. 1 comma 3 is on our graph. So if we were to plug in -1 now, I think that at this point it'd be wiser to use synthetic substitution. So we say dropping in coefficients. I want you to notice this here. We get a -1x to the fourth, a -2x to the third, a +2x to the second, a +4x, and 0. You have to put in the 0 here for this 0 if you're going to do synthetic. So now if I'm plugging in, say, 2, let's see what we get here. Dropping this down, we get -1. We get 2 times -1 is -2, plus this is -4. -4 times a +2 is -8, plus a +2 is -6, times a 2 is -12, plus a 4 here is -8, and -8 times 2 is -16, plus a 0 is -16. So we're going to put a -16. Let me get all this stuff out of the way. A -16 here, which I want you to notice this. 2 comma -16 is going to be so far down here that you're not going to be able to graph it, but it gives us an idea that our graph does something like this. It leaves very steeply. Okay. So now when we plug in -1, let's try this again. Let's try with -1 instead of a 2. So we say -1. -1 times -1 is 1. 1 plus a -2 is -1. Times a -1 is a 1. Plus a 2 is a 3. Times a -1 is a -3. Plus a 4 is a 1. Times a -1 is -1. Plus a 0 is -1. So this time we get a -1 when we plugged in -1. So we get -1. So -1 is on our graph right here. We can say, what if I plugged in -2? So -2, plug in a -2 out here. We say -2 times a -1 is a 2. Plus a -2 is a 0. Times -2 is a 0. Plus a 2 is a 2. Times a -2 is -4. -4 plus a +4 is a 0. -2 times 0 is 0. 0 plus 0 is 0. So we get 0 here. So this is a point on our graph. -2, 0. Okay. So we should probably plug in a -3. The only reason I say this is because I can see how my graph is doing this here. What you're going to find out when you plug in -3 and -4, I'll let you do that, is you're going to get a grid that actually, a graph that has to go back down again on the left. But you'll get something like this. So I'll leave it up to the viewer to find this, but that's how you sketch polynomial functions in general. Cheers.